Welcome everyone to this technical explainer. Today, we're diving into something absolutely crucial for the mechanical engineering and piping design community. We are unpacking the ASTM B474 specification. Look, if your work involves designing, procuring, or operating systems that handle unforgiving environments, you need to know exactly what this standard demands.
It's the ultimate engineering challenge, isn't it? How do you pipe the impossible? We're talking about containing extremely corrosive media, highly toxic acids, and operating at blisteringly high temperatures safely and reliably, year after year. Standard carbon steel? No way, it won't survive. Even basic stainless grades are going to fail under these localized attacks. You need something much more robust. And more importantly, you need a manufacturing standard that guarantees the integrity of every single weld. Okay, so let's break this down. ASTM B474 is the standard specification for electric fusion welded nickel and nickel alloy pipe. This standard is written specifically for high temperature or highly corrosive service. It dictates the production of pipes using electric fusion welding for some of the most resilient materials on the planet. We're talking alloys like alloy 20, Inconel, and Incolloy. When the environment is hostile, B474 is literally the blueprint for the pipe that's going to survive it.
Here is a quick roadmap of what we'll cover today. 1. What is ASTM B474? 2. Welding classes and fabrication. 3. Alloy chemical compositions. 4. Mechanical properties and stress. 5. Testing and quality control. And 6. Real-world procurement specs.
All right, jumping right into Section 1, what is ASTM B474?
Let's start right at the top to understand the foundational requirements. What's really fascinating here is the sheer rigor demanded by the standard. B474 strictly covers electric fusion welded, or EFW pipe. The fabrication requires full penetration double welded or single welded butt joints. But it doesn't just stop at the physical weld. The standard actually mandates chemical analysis for both the base plate and the deposited weld metal. We can't have any dilution compromising that corrosion resistance. Furthermore, it requires highly specific heat treatments, like solution annealing or stabilized annealing, dictated precisely by the specific alloy being processed.
Moving on to Section 2, welding classes and fabrication.
Look, not all fusion welds are created equal, so the standard categorizes varying levels of penetration and radiographic inspection. The absolute crucial point here is knowing which of these 5 classes to specify for your system. Class 1 is your gold standard, double welded, using filler metal in all passes, with 100% complete radiography. Class 2 gives you that double weld but drops the radiography requirement. Class 3 is single welded with complete radiography. Class 4 is basically like Class 3, except the inside pass can be made without filler metal. And finally, Class 5 gives you a double weld but with only spot radiography. Your choice of filler passes and examination here literally dictates your pipe's safety factor and critical service.
Let's hit Section 3, alloy chemical compositions.
This is where the material science takes over, and it brilliantly illustrates the metallurgical differences between two heavyweight alloys governed by B474, Incolloy 825 and Inconel 625. Just look at the molybdenum levels. Incolloy 825 has 2.5 to 3.5%, which is great for resisting pitting and crevice corrosion. But Inconel 625? It packs a massive 8 to 10% molybdenum, alongside a minimum 58% nickel content. Contrast that with 825's balanced iron-nickel matrix, which requires at least 22% iron. These chemical differences fundamentally change where and how you're going to deploy them. So to put that chemistry into practical, real-world procurement terms, Incolloy 825 is basically your go-to workhorse for mixed acid chemical processing. It beautifully resists sulfuric and phosphoric acids, and it's generally more cost-effective when your primary enemy is aqueous corrosion. On the flip side, Inconel 625 is what you prioritize when you need extreme strength and toughness at elevated temperatures, and we're talking up to 2,000 degrees Fahrenheit. The high nickel and molybdenum in 625 stiffen the alloy matrix, giving it incredible structural integrity in the absolute worst conditions.
All right, Section 4, mechanical properties and stress.
Chemical resistance is awesome, but at the end of the day, the pipe has to hold pressure. The standard establishes strict baseline mechanical requirements. Take alloy 20, for example. You need a minimum tensile strength of 80 ksi and a minimum yield strength of 35 ksi. What's absolutely vital for design tolerances here is how that yield is determined. B474 specifies using the 0.2% offset method, though an alternative 0.5% total extension under load is permitted. And minimum elongation? It must be at least 30% in a 2-inch gauge length. You have to ensure these numbers are verified on your mill test certificates.
Let's see how these baselines translate into real-world engineering design. Think about maximum allowable stress, or MAS, values for alloy 20 sourced directly from the ASME boiler and pressure vessel code. Notice how the allowable stress degrades as the operating temperatures approach 800 degrees Fahrenheit. For MAS Group 3, which includes B464 welded pipe, the allowable stress drops from 19.4 KSI at ambient temperatures all the way down to just 14.3 KSI at 800 degrees. If you aren't accounting for this thermal derating in your piping flexibility analysis, your system is definitely at risk.
Section 5. Testing and Quality Control.
So, how do we prove the pipe actually meets the standard before it ever leaves the mill? Well, B474 mandates a really rigorous suite of QA/QC protocols. Every pipe must pass a transverse guided weld bend test and detention test. If a specimen breaks because of a flaw outside the gauge length, there are strict retest parameters allowed. Radiography is mandated depending on the class you specified. Plus, for sensitized alloy 20, that's UNS N08020, a specific intergranular corrosion test per lot is absolutely mandatory. And of course, every single piece must undergo a hydrostatic pressure test.
Let's quickly break down the math for that hydrostatic test. The formula is P equals 2ST over D. P is your test pressure. S represents the allowable fiber stress, which the standard pegs at a constant 20,000 psi for this calculation. Little t is your specified wall thickness, and D is your specified outside diameter.
But the standard places strict operational limits on this test. The test pressure has to be held for a minimum of 5 seconds. However, there are pressure caps you cannot exceed, regardless of what the math says. For nominal pipe sizes 3 inches and under, the maximum test pressure is capped at 2,500 psi. For sizes over 3 inches, the cap is 2,800 psi. This is to ensure you don't accidentally yield the pipe during the very test that's meant to prove its integrity.
Finally, Section 6, Real-World Procurement Specs.
How do major energy operators actually turn this theoretical standard into a binding purchase order? To illustrate this, let's look at internal procurement guidelines from PetroSA, the South African national oil company. Major operators don't just ask for ASTM B474 pipe. No, they utilize these ASTM guidelines as the foundation, and then they build their own rigorous internal engineering specifications right on top of them to guarantee safety and traceability.
Looking at the PetroSA scope, this document acts as a direct supplement to the purchase order. It strictly defines the technical requirements for the manufacture, examination, testing, identification, and documentation of the pipe. They lock down the exact expectations so there is absolutely zero ambiguity for the manufacturer.
PetroSA's receiving rules are totally uncompromising. Mill markings must explicitly include the heat number, ensuring strict heat-to-piece traceability. Upon receipt, they mandate positive material identification, or PMI, to verify the alloy chemistry right on the dock. Furthermore, any required color coding must be applied only by the pipe mill itself, never by a third-party supplier or stocktist. Why? Because strict traceability prevents catastrophic material mix-ups on site. If these rules aren't met, the non-conforming materials are immediately rejected and returned at the supplier's cost.
Which brings us to the final thought I want to leave you with today. As operating temperatures continue to rise across industrial sectors and processing environments just grow increasingly toxic and corrosive, are your internal piping specifications truly ready for the future? Are you leveraging the full power and precision of standards like ASTM B474? Take a hard look at your procurement documents and make sure you aren't leaving your system's integrity to chance. Thank you for joining me for this explainer, and keep engineering the impossible.